Last time, right at the end, you said something that I've been turning over ever since. We were talking about Emmy Noether, about how symmetry hands you conservation laws, and you pushed it one step further. You said that if you demand a certain symmetry hold at every point in space independently, the mathematics forces a whole field into existence to keep it true, and that field is the electromagnetic field. You said electromagnetism is the first, cleanest case of a symmetry giving birth to a force and to light itself. And then you just left me there. So today I want the actual thing. George, what is the electromagnetic field, and how on earth does it turn out to be light?
Today we cash that check in full, and it's one of the greatest stories in all of physics, because it's the first time humanity took two things that looked completely unrelated and discovered they were one thing, and then got, for free, a third thing nobody was even looking for. The two things are electricity and magnetism. The person who united them is James Clerk Maxwell, working in the 1860s. And the third thing, the one that falls out unbidden at the end, is light. By the time we're done, I want you to see how four statements about two invisible fields not only married electricity to magnetism, but revealed that the light streaming from your lamp is the very same phenomenon, just vibrating.
Start me before Maxwell then, because I want to feel the two separate things part. In my head, electricity and magnetism are obviously related. I've seen an electromagnet. But you're saying that wasn't obvious at all.
It genuinely wasn't, and for most of history, they were studied by different people asking different questions. Electricity was the business of rubbed amber and sparks, and later, batteries and currents in wires. The science of charge, of stuff that attracts and repels. Magnetism was the business of lodestones and compass needles, naturally magnetic rocks that pointed north, seemingly a completely separate curiosity about a different kind of attraction. For centuries, there was no reason to think a spark and a compass needle had anything to do with each other. They were two subjects in two different chapters of the book.
So what cracked it? What was the first hint that the two chapters were secretly about the same thing?
Two beautiful experimental clues about a decade apart, early in the 1800s. The first, a Danish physicist named Ørsted was lecturing, ran an electric current through a wire, and noticed a compass needle sitting nearby twitch and swing to point across the wire. Electricity had reached out and moved a magnet. A current, moving charge, produces a magnetic effect around it. That's the first bridge. Electricity can make magnetism. The second clue came from Michael Faraday, one of the great experimenters who ever lived, who asked the obvious reverse question. If electricity makes magnetism, can magnetism make electricity? And he found that if you take a magnet and move it near a coil of wire, crucially move it, change things, a current flows in the coil. So magnetism, changing in time, can make electricity. The two subjects were reaching into each other's territory, but it was still a set of disconnected effects, a pile of related tricks, with no single framework holding them together.
And Maxwell's job was to build the framework, the thing that holds all the tricks in one hand.
Exactly. And here's how he did it, because the strategy matters as much as the result. Maxwell worked with two fields. Now, field is the key idea, so let me make it concrete. A field is just a quantity that has a value everywhere in space. Picture the electric field as a set of invisible arrows filling all of space, each arrow telling a charge placed there which way it would be pushed and how hard. That's the electric field. Call it E. And picture a second set of arrows, the magnetic field, call it B, telling a compass needle which way to point at each location. Two fields, E and B, defined at every point in space, everywhere, all the time. Maxwell's move was to write down the complete set of rules governing how charges and currents produce these two fields, and how the fields interweave with each other. And the astonishing thing is that the entire subject, every spark, every magnet, every clue Ørsted and Faraday found, compresses into just 4 statements, 4 equations. Let me walk you through them one at a time, in plain words.
Please. And go slowly because I want to actually hold each one, not just let them wash over me.
We'll take them one at a time and tie each to something you can picture. The first equation is about the electric field and where it comes from. It says, electric charges are the sources of the electric field. Put a positive charge somewhere, and electric field arrows point outward from it in all directions, like quills on a hedgehog. Put a negative charge, and they point inward toward it. The field lines begin on positive charges and end on negative charges. That's the first law, sometimes called Gauss's law for electricity, and its content is simply charge makes the electric field, and you can tell where the charges are by watching where the field lines start and stop.
Okay, that one matches my intuition. Charges are the little fountains and drains that the electric field pours out of and into. What's the second?
The second equation is the same kind of statement, but for the magnetic field, and it contains a startling twist by way of what it forbids. It says, there are no magnetic charges, no sources, no drains for the magnetic field. In electricity, you have isolated positive and negative charges, a lone plus, a lone minus. But there is no such thing as an isolated north pole or an isolated south pole. Every magnet, no matter how you cut it, always has both a north and a south. Snap a bar magnet in half, hoping to get a separate north piece, and you just get 2 smaller complete magnets, each with its own north and south. So magnetic field lines never begin or end anywhere. They have no fountains or drains to start or stop on. Instead, they always form closed loops, running out of the north, around, and back into the south, threading through the magnet to close the circuit. The second law is, magnetic field lines never end. No magnetic monopoles, so far as anyone has ever found.
That's a strange and specific thing for a law to say. This particular object doesn't exist. Why is it worth enshrining that there are no lone magnetic poles?
Because it's a deep structural fact about the magnetic field, and it makes the 2 Gauss laws into a matched, asymmetric pair that you should hold side by side. Electric field has sources, the charges, so its lines start and stop. Magnetic field has no sources, so its lines can only loop. That contrast, E springs from charges, B only circulates, is woven right through the rest of the story, and it's exactly why, as we'll see, the magnetic field is fundamentally a thing that goes around rather than out. And people do search for magnetic monopoles to this day. If one were ever found, this second equation would need a new term. So far, nothing. The magnetic field loops, always.
2 down. Electric fields spring from charges. Magnetic fields only make loops. I have a feeling the last 2 are where the action is, because you keep hinting at change and motion.
You have exactly the right instinct, because the first 2 equations are about static situations. Charges sitting there, magnets sitting there. The last 2 are about change, about things varying in time, and that's where the whole universe comes alive. The third equation is Faraday's discovery, made into law. It says, a changing magnetic field creates a circulating electric field. If the magnetic field passing through a region grows or shrinks or shifts, if it changes, then it conjures an electric field that whirls around it in a loop. And this isn't abstract, it is the basis of the entire electrical world you live in. Every generator in every power plant is a magnet and a coil in relative motion, using exactly this law. Changing magnetic field makes circulating electric field, which drives current, to turn mechanical motion into electricity. When you plug anything into the wall, you are drinking from Faraday's third equation.
Before you give me the fourth, make Faraday's law physical for me first. Why does it have to be a changing magnetic field? Why doesn't a strong, steady magnet just drive a current through a nearby wire on its own?
That word, changing, is the entire soul of the law, so it's worth pausing on. Take the most powerful magnet you can lift and set it right next to a coil of wire, perfectly still. Nothing happens. No current, none, no matter how strong the magnet. The coil doesn't care how much magnetic field is passing through it. It only responds to the field changing. Now move that magnet, shove it toward the coil, or yank it away, and while it's moving, current flows. Stop moving it, and the current stops instantly, even though the magnet is still sitting there, drenching the coil in field. It's the rate of change that drives the current. Move the magnet faster, get a bigger current. And this is not a footnote, it dictates the entire design of the electrical world. It's why a generator has to spin. The spinning constantly re-changes the magnetic field through its coils. It's why the power grid runs on alternating current that reverses many times a second, because only a continually changing field keeps inducing. It's why a bicycle dynamo has to turn to light your lamp. Nature hands you no electricity for a magnetic field just sitting there. It pays out only for change.
So the third law is the one humming inside every power station. A changing magnetic field pushes electric charge around in a loop. What's the fourth?
The fourth equation is where Maxwell earns his immortality. So let me build it in 2 stages, because it started as somebody else's law, and Maxwell fixed it in a way that changed the world. The first stage is Ampere's law, already known before Maxwell. An electric current, charge flowing through a wire, creates a magnetic field that circles around it. That's Ørsted's compass, made quantitative. It's why a coil of current-carrying wire acts as an electromagnet, with magnetic field looping around the flowing charge. So, current makes a circulating magnetic field. Good. But Maxwell, staring at this equation, noticed something was broken. In a specific situation, the law contradicted itself. It gave 2 different answers for the same magnetic field, depending on how you looked at it. And worse, it quietly violated the conservation of electric charge, which we know from last time is sacred and tied to a symmetry. The law as it stood was mathematically inconsistent.
Wait, so this isn't a story about a new experiment revealing something. Maxwell found a flaw in the math itself.
That is precisely the point, and it's what makes this one of the most remarkable moves in the history of science. Maxwell was not led by a surprising measurement. He was led by an inconsistency on paper, a term missing from an equation, demanded by nothing but the requirement that the mathematics be coherent and that charge be conserved. And to fix it, he added a new term to Ampere's law, a term saying, just as a current creates a circulating magnetic field, so too does a changing electric field. A place where the electric field is growing or shrinking in time produces a magnetic field looping around it, exactly as if a current were flowing there, even through empty space where no charge moves at all. He called this the displacement current, and he added it not because an experiment forced him to, but because the equations could not be consistent without it.
Can you actually show me the crack he caught? I don't want to just be told the equation was inconsistent. I want to see the contradiction with my own eyes.
I can, and it's a lovely, almost geometric flaw once you see it. Ampere's law, in its original form, says something subtle about surfaces. It says, the magnetic field circling around a chosen loop is determined by the electric current passing through any surface you stretch across that loop. And it shouldn't matter which surface you pick, flat or bulging, as long as its edge is that same loop. Now here's the setup that breaks it. Picture a capacitor charging, 2 metal plates with a gap between them, and a wire carrying current up to one plate, piling charge onto it. Draw a loop around the wire, just below the plate, and ask for the magnetic field around that loop. Choose the obvious flat surface, a little disc capping the loop. The wire punches straight through it, current passes, and Ampere's law gives you a magnetic field. Fine, but now choose a different surface with the very same edge. A surface that balloons upward and dips into the gap between the plates instead of cutting the wire. No charge flows across that gap, it's a gap. So through this surface, zero current passes, and Ampere's law says the magnetic field should be zero. Same loop, two surfaces, two different answers. And a magnetic field can't be two things at once.
So the law gives you a real answer or nothing at all, depending on which imaginary surface you happen to draw. That's obviously broken. How does Maxwell's new term rescue it?
Beautifully, and this is where the displacement current earns its keep. Look at what's happening in that gap between the plates. As charge piles up on the plate, the electric field between the plates grows. It's changing, and changing fast, precisely while the capacitor charges. Maxwell's added term says that changing electric field acts exactly like a current for the purpose of making a magnetic field. So through the ballooning surface that dips into the gap, there's no actual charge flow, but there is a changing electric field, and by the new term, it contributes just the right amount, exactly equal to the current through the flat surface. Both surfaces now give the identical magnetic field. The contradiction is stitched shut. And notice what he'd been forced to introduce to close a bookkeeping wound: the statement that a changing electric field makes a magnetic field, which is the very ingredient that, in a moment, lets light exist. He fixed a leak and uncorked the ocean.
Let me make sure I've got the symmetry of it, because it's suddenly beautiful. The third law says a changing magnetic field makes a circulating electric field. And Maxwell's new term in the fourth law says a changing electric field makes a circulating magnetic field. They mirror each other.
You have just seen the whole thing, and the fact that you notice the mirror is exactly why what happens next happens. Hold those two facing statements together. A changing B makes a circling E. A changing E makes a circling B. Now, Maxwell, being the kind of mind he was, asked the inevitable next question. What if you had both at once, feeding each other, out in empty space, far from any wire or magnet? Suppose the electric field somewhere changes. By the fourth law, that creates a magnetic field. But that magnetic field is itself springing into being. It's changing. And by the third law, a changing magnetic field creates an electric field, which is itself changing, and so, by the fourth law again, it creates a magnetic field. Do you see what he'd found? A self-sustaining chain. Each field, by changing, regenerates the other, over and over, with no charges and no wires needed to keep it going.
It's like the two fields are leapfrogging through empty space, each one's collapse feeding the other's birth, hand over hand. That can't just sit still, it would have to travel.
It travels. That leapfrogging pattern of electric and magnetic fields, each sustaining the other, propagates through empty space as a wave, an electromagnetic wave. And this is the moment everything changes, because Maxwell could do more than describe the wave qualitatively. He could take his four equations and, with the displacement current term now in place, derive the exact speed at which this self-sustaining disturbance must travel. The speed came out as a specific combination of two numbers, two constants that were already sitting in the equations, both of which had been measured in the laboratory years earlier by people doing ordinary experiments with charges and with magnets.
Tell me about those two constants, because I want to feel where the number comes from.
They're wonderfully mundane in origin, which is what makes the ending so dramatic. The first constant measures how strongly electric charges push on each other. You can pin it down with a careful tabletop experiment involving charged objects and the forces between them. It's called the electric constant. The second measures how strongly currents push on each other magnetically. You get it from an experiment with current-carrying wires and the magnetic forces between them. It's called the magnetic constant. One number from electrostatics, one number from magnetism, each measured independently on the bench by people who had never dreamed of light. And Maxwell's derivation said the speed of his electromagnetic wave is 1 over the square root of the product of those two constants. So he plugged in the two measured numbers and turned the crank.
And what came out?
What came out was about 300,000 kilometers a second. And Maxwell knew that number. Everyone knew that number. It was the measured speed of light, determined by astronomers and by optical experiments over the preceding decades, a figure from a completely different branch of science. Optics, the study of lenses and beams and the shimmer of light. His electromagnetic wave, built from nothing but charges and magnets and a consistency fix, traveled at exactly the speed of light. And Maxwell drew the only conclusion a person could draw. He wrote, in effect, that the agreement was too perfect to be coincidence, that light itself must be an electromagnetic wave, a ripple in the very electric and magnetic fields he'd been studying.
That gives me chills, actually. He wasn't looking for light. He was fixing a broken equation about magnets and currents, and light fell out of the repair.
That's the heart of it, and it's why this is held up as maybe the single greatest theoretical prediction before the 20th century. Three sciences that had been separate for all of human history, electricity, magnetism, and optics, collapsed into one. Light was revealed to be not its own mysterious substance, but a self-propagating disturbance in the electromagnetic field, an oscillation of E and B leapfrogging through space at the speed his equations demanded. The lamp on your desk, the sunlight through your window, the glow of every star, all of it is electric and magnetic fields, trembling, moving, exactly as Maxwell's four statements require. Optics became a branch of electromagnetism in a single stroke.
Let me picture the wave itself more precisely before we go on. What exactly is waving, and does it need something to travel through, the way sound needs air to carry it?
Two questions, and both answers are illuminating. First, what's waving? At each point along the wave, there's an electric field arrow and a magnetic field arrow, and they sit at right angles to each other. And both of them are at right angles to the direction the wave is traveling. So nothing is moving back and forth along the line of travel. The fields waggle side to side, crosswise, while the whole pattern races forward. That makes light a transverse wave, like a ripple shaken along a rope, not a squeeze and stretch wave like sound. The electric field oscillates up and down, say, the magnetic field oscillates side to side, and the wave shoots straight ahead, the two fields forever perpendicular, forever regenerating each other. Now the second question, and it's the profound one. Sound needs air. Ocean waves need water. Every wave people knew before Maxwell was a disturbance in some material medium. So everyone assumed light, being a wave, must also be a vibration in something. They even named the hypothetical substance the ether, an invisible jelly filling all of space for light to wave through. But Maxwell's wave needs no medium at all. Each field creates the other. The wave carries its own means of propagation on its back. It sails through perfect vacuum, through utterly empty space, waving through nothing but itself.
So the ether, the stuff everyone assumed light waved through, just isn't there. The wave is self-supporting.
It isn't there, and that absence became one of the most important discoveries in physics. People searched hard for the ether. They reasoned that as the Earth plows through it on its orbit, there should be an ether wind that makes light travel a touch faster or slower depending on direction. The most careful versions of that experiment found absolutely nothing. No ether wind, no medium, no preferred frame for light to wave in. Light simply travels through emptiness at its fixed speed, the same in every direction. And hold on to that null result, because it's the second time in this episode we've bumped into something pointing straight at Einstein. That stubborn, medium-free, same in all directions speed is exactly the puzzle relativity had to resolve. For now, the picture to carry is a self-sufficient crosswise ripple of two perpendicular fields, needing nothing to travel through, which is precisely why the light of distant galaxies can cross billions of years of empty space to land in a telescope.
So, if visible light is just oscillating electric and magnetic fields traveling at that speed, is there anything special about visible light, or is it one note in a much bigger range?
You've reached the next gift, and it's enormous. There is nothing special about visible light except that our eyes happen to respond to it. Maxwell's equations permit an electromagnetic wave of any wavelength at all. The fields can leapfrog with long, lazy oscillations or short, frantic ones, and every one of them travels at the same speed. Visible light occupies a tiny slice of that range. Stretch the wavelength longer and you get infrared, then microwaves, then radio waves. Same phenomenon, same equations, same speed, just oscillating more slowly over longer distances. Squeeze the wavelength shorter than visible and you get ultraviolet, then X-rays, then gamma rays. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. It is all one single thing, the electromagnetic wave appearing across an unbroken spectrum. The radio bringing you music, and the X-ray imaging your bones and the warmth you feel from a fire, and the color of the sky are the identical physical phenomenon, differing only in how tightly the fields are oscillating. Maxwell didn't just explain light, he predicted an entire spectrum of invisible light nobody had catalogued.
And I assume somebody eventually went and found the invisible parts to prove Maxwell wasn't just doing beautiful math.
They did, and it's the proper end of the experimental story. About 2 decades after Maxwell, in the 1880s, a physicist named Heinrich Hertz set out to manufacture and detect electromagnetic waves that were not light, to make Maxwell's prediction tangible. Using electric sparks, he generated invisible waves in his laboratory, sent them across the room, and detected them on the far side. And he measured their speed and their properties and found they behaved exactly as Maxwell's equations said they must, traveling at the speed of light. Those were radio waves, the first ever deliberately produced and received. Hertz had confirmed that Maxwell's invisible electromagnetic waves were real. Within a couple of decades, that discovery became radio, then television, then every wireless thing we own. The entire wireless world is Hertz confirming Maxwell's repaired equation.
You keep calling the field real, the electromagnetic field, the thing that's waving. But it's invisible, and I could imagine it's just a convenient way of bookkeeping the forces between charges. In what sense is the field a real physical thing rather than an accounting trick?
This is the right challenge to press, and Maxwell's framework gives a decisive answer. The field is real because it carries energy and momentum of its own, independent of any charges. Think about the sunlight warming your face. That energy was manufactured in the sun, left its surface, and traveled for about 8 minutes across nearly 150 million kilometers of empty space. Space with no charges in it, nothing but field, before depositing its warmth on your skin. Where was that energy during those 8 minutes of transit? It was in the field. The electromagnetic field held it and ferried it across the void. Energy in flight, stored in nothing but E and B. An accounting trick can't warm your face from across the solar system.
That's a strong point. The energy has to be somewhere while it's in transit, and there's nothing out there but the field to hold it. You said momentum too. The field carries momentum?
It does, and this one you can almost feel. Light pushes. When an electromagnetic wave lands on a surface, it delivers not just energy, but a tiny shove, a real pressure called radiation pressure. It's feeble for everyday light, which is why you don't feel sunbeams knocking you over, but it's genuinely there, and it has muscle at scale. It's the principle behind a solar sail. A spacecraft with a large, thin mirror can be pushed through space by sunlight alone. No fuel, just the momentum of light pressing on the sail. It's part of why a comet's tail streams away from the sun rather than trailing behind the comet's motion. Sunlight is physically pushing the dust outward. A pure bookkeeping device cannot drive a spaceship or blow a comet's tail across the sky. The field carries momentum because it is a physical entity, as real as matter, just made of neither charge nor stuff. And that realization that the field is a thing in its own right, holding energy and momentum, obeying its own equations, is the template for all of modern physics. Every fundamental force we know is now described as a field filling space.
I want to come back to something because you planted 2 seeds earlier and I don't want them to go unharvested. You said this whole thing connects back to our very first Great Papers episode on Einstein and relativity. How does Maxwell lead to Einstein?
This is one of the most consequential threads in all of physics, and you're right to pull it. Look again at what Maxwell's equations say about the speed of light. They don't say light travels at that speed relative to some particular thing, relative to its source, or to the air, or to an observer. The speed simply falls out of the 2 constants of nature as a fixed number, full stop. But that's deeply strange, and here's why. In ordinary life, speeds add. If you throw a ball forward from a moving train, someone on the ground sees the ball moving at the train's speed, plus the throw's speed. Common sense says every speed should depend on who's measuring and how they're moving. But Maxwell's equations stubbornly give the same single speed for light no matter what, with no relative to attached. That clash between everyday velocity addition and the fixed speed baked into electromagnetism was a crack running through physics, and it's precisely the crack the young Einstein walked into. He took Maxwell's equations at their word. The speed of light really is the same for every observer, however they move, and forcing the rest of physics to be consistent with that one demand is exactly what produced special relativity, the collapse of absolute time, the whole thing we spent that first episode on. Special relativity is, in a real sense, the universe insisting that Maxwell's equations are right for everybody.
So relativity is the price the rest of physics had to pay to keep Maxwell's fixed speed of light true for everyone. That's a stunning amount of consequence from one repaired equation. What was the other seed? You mentioned last time symmetry too.
The other seed ties us straight back to Noether and gives this whole episode its bookend. Remember the promise from last time? Gauge symmetry gives you conservation of charge. Now we can name where that symmetry lives. It turns out you can repackage Maxwell's electric and magnetic fields in terms of underlying quantities called potentials, a kind of scaffolding beneath the fields. And these potentials have a curious freedom. You can adjust them in a particular coordinated way, all through space, without changing the actual electric and magnetic fields at all, and therefore without changing anything you could ever measure. That freedom to reshuffle the potentials with no physical consequence is precisely the gauge symmetry we invoked last time. And by Noether's theorem, that continuous symmetry hands you a conserved quantity, which turns out to be electric charge. So the conservation of charge, one of the bedrock facts of physics, is the shadow cast by a hidden symmetry inside Maxwell's own equations. The 2 tutorials fit together like a key in a lock. Noether told us symmetry breeds conservation. Maxwell is where you actually see the electromagnetic symmetry doing it.
That is a genuinely satisfying click. The abstract theorem from last time landing on a concrete, testable law right here. Let me try to gather the whole arc, the way we do, and you catch my errors. Before Maxwell, electricity and magnetism were 2 separate sciences, loosely bridged by Ørsted and Faraday. Maxwell captured everything in 4 statements about 2 fields. Electric field lines start and end on charges. Magnetic field lines never end, they only loop. A changing magnetic field makes a circulating electric field, which runs our generators, and currents, plus, by Maxwell's decisive fix, changing electric fields, make circulating magnetic fields. That last added term let the 2 fields sustain each other and travel as a wave, whose speed, computed from 2 bench-measured constants, came out exactly equal to the speed of light. So light is an electromagnetic wave. one note in a whole spectrum from radio to gamma. And it reaches forward into relativity and backward into Noether's symmetry.
That is the entire thing, captured cleanly, and the sentence I'd want you to carry out is this. Maxwell took two forces and a repaired equation and discovered that light is not a separate substance in the universe, but a self-sustaining ripple in the electric and magnetic fields, moving at a speed the equations themselves dictate. Electricity, magnetism, and light, one phenomenon. That unification became the template for how physics has proceeded ever since. Find the field, write its equations, and see what waves it supports. It's how we understand every force today.
From 2 chapters in a book to a single sentence about trembling fields. But you dangled one more thing at the very start, and I won't let it go either. You said light being a wave is only half the story. What's the other half?
The other half is the door to everything we'll do next, and it's this. Maxwell settled, apparently for all time, that light is a wave, a smooth, continuous, spread-out oscillation of fields. And he was right. But within a few decades, physics discovered that light is also, somehow, a stream of discrete particles, little indivisible packets of energy we call photons. Light is both at once, a wave that also arrives in lumps. That impossible-sounding duality, wave and particle in the same breath, is exactly where the quantum revolution begins, and it doesn't stay confined to light. It turns out that electrons, atoms, matter itself, all share it. So the next time we meet, we'll follow that thread straight into the strangest and most successful idea in physics, that everything, light and matter alike, is described by a wave function, obeying an equation written down by Schrödinger. Maxwell gave us the wave of light. Next, we'll find the wave hiding inside all of matter.
The wave of light, and then the wave inside everything else. That's a hook I'll be thinking about all week. Thank you, George. Next time, the wave function and Schrödinger's equation. For now, electricity, magnetism, and light are one, and Maxwell heard the whole spectrum in 4 short lines.